Good morning, all. This is Dr. P. Ravindra Kumar, Professor, Department of Mechanical Engineering, Lecturer, Baladi College of Engineering. So this is lecture number 25. In last class, I have covered some of the basic problems connected to the second law of thermodynamics. And in this lecture also, some more problems are yet to cover. So the outcome from this particular course, at the end of listening this particular second law of thermodynamics topic, now the student is going to apply the second law of thermodynamics to solve the performance parameters of a mechanical system. So what are the performance parameters of a mechanical system? Coefficient of performance, heat supply, heat rejection, work output, work input, energy efficiency rating, right? Efficiency, coefficient of performance to the heat engine, refrigerator, heat pump, solar energy level, right? So all the realistic day-to-day connected mechanical problems. So today I am going to cover these are the problems. So one is this is the thing what he has to understand. A refrigerator, if a refrigerator is used for heating purposes in winter, if a refrigerator is used for heating purposes in winter, so that the atmosphere becomes the cold body and the room to be heated becomes the hot body, how much heat would be available for heating for each kilowatt? See here, for each kilowatt, that is W is given for each kilowatt work input, that means 1 kilowatt to the driving motor, If the COP of the refrigerator is given as a COP is 5 and the electromechanical efficiency of the motor is 90%, how does this compare with the resistance heating? How does this compare with the resistance heating? Clear? So in this particular problem here, if you just observe that, what is the coefficient of performance of a refrigerator? The coefficient of performance of the refrigerator is nothing but it is defined as the ratio of desired effect to the work spent to the work input. See, observe this one, right? So the COP of a, and already we know that the COP of a heat pump is equal to the COP of a refrigerator plus 1. Refrigerator plus 1. So here, try to understand the problem. A refrigerator is used for heating purposes in winter. A refrigerator is used for heating purposes in winter. Try to understand this particular thing, right? So that means it is going to come out as a heat pump problem. So the COP of refrigerator is given as a 5 plus 1, that is equal to 6. Then what about this 6? The desired effect, try to draw the diagram. Though the diagram is not there in the textbook, but try to understand these particular things. So observe the directions. This is Q2 and the heat pump. That means the refrigerator is used for heating purposes. So this is the room, right? And this is to be maintained at a higher temperature. So the desired effect. So this is the source T1 and this is the sink T2. So the desired effect for the heat pump is this one, right? So that is nothing but equal to Q1 divided by W. So this W already it is given the W. What is that particular? So that is equal to here the input. So W is equal to Q1 divided by 6. Q1 divided by 6. But the motor efficiency. So here the motor efficiency is 90% to operate the condition, right? So to operate that one. So the motor energy efficiency, the motor efficiency is equal to, or the electrical efficiency is equal to the work divided by, that is 90%, 0.9, right? So that is nothing but equal to that work Q1 divided by zero point 0.9 into 6, 0.9 into 6. So you will get this value as 0.1852 Q1. That is Q1, right? So it is given that for each kilowatt, it is given that here the efficiency, that is what about here if you consider this particular thing. So almost all it is 18.52%. 18.52% of heat, that is for the, that it is used for the direct heating, that it is used for the direct heating. Then heating, so that the atmosphere becomes cold body and the room to be heated becomes the hot body. So this is the room becomes the hot body, that is this is going to become the hot body. And how much heat would be available for heating kilowatt input to the driving motor? How much heat would be available for heating for each kilowatt input to the driving motor? The COP of the refrigerator is this one, and the electromechanical efficiency of the motor is this one, 90%. How does this compare with the resistance heating? How does this compare with the resistance heating? So now, how does you are going to compare that with the resistance heating? Q1 is equal to, so 18.52% is given, right? So that is for each kilowatt, that is 1 divided by 18.52 divided by 100. 18.52 divided by 100, right? So 18.52 divided by 100, then it is going to come out as 5.5.39, 5.39 kilowatts, 5.39 kilowatts, right? So this is how you have to solve the problem. So the understanding of the problem is very important this side. So if you just think of that, yes, refrigerator is given, then directly applying the refrigerator problem and solving the COP and getting the answer, it is completely going to become wrong. So though the refrigerator is given here, but if a refrigerator is used for heating purposes in winter, so that the atmosphere becomes the cold body. So this is going to become the cold body. And the room to be heated becomes the hot body, this one. How much heat would be available for heating each kilowatt input to the driving of a motor, right? So the problems to be solved in this way. So the refrigerator problems are over, heat engine problems are over, heat pump problems are completed, and the combination of the heat engine and the refrigerator, that problem is also over. Sometimes you may get the combination of a problem. So try to understand that particular combination of the problem. So here the second one is using the engine of 30%, using an engine of 30% thermal efficiency to drive a refrigerator having a COP of 5. To drive a refrigerator having a COP of 5. Then what is the heat input to the engine for each megajoule? See here. What is the heat input into the engine for each megajoule, that is work is for each megajoule removed from the cold body, right? So that is here each megajoule removed from the cold body by the refrigerator. So when the refrigerator is mentioned, so try to draw the things. So the first and foremost thing what you have to do is that practicing this particular case, then you can simplify the thing. So this is the W, and the other directions are so in the same way you need to practice the same thing in the same thing. Then here how you can sort it out using the engine of 30% thermal efficiency. So the efficiency of a heat engine is that is 30%. So 0.30 is equal to W divided by Q1. W divided by Q1. W divided by Q1. Then what is Q1? And this is also an engine of 30% thermal efficiency to drive a refrigerator of COP. So drive a refrigerator of COP. So that means Q2. Here the desired effect is this one. So that it is Q2 by W. Q2 by W. But the heat pump, the refrigerator, it is given as a 5. It is given as a 5. So for each megajoule removed from the cold body, we need the work input. We need, that is, some work input is required. Some work input is required. So what is that one? Here, W is equal to Q2 divided by COP of a refrigerator. So what is that? For each heat input to the engine, for each megajoule removed from the cold body, that means this one. What is that? It is megajoule. 1 megajoule. So that is equal to 1 megajoule divided by 5. So you will get it as 200 kilojoule. So 1 megajoule is equal to 1 megajoule is equal to 1000 kilojoule. 1000 divided by 5. So you will get it as a 200 kilojoule. 200 kilojoule. So with this one, once after getting this particular W value, then what about the Q1 value? So that is Q1 is equal to here. Q1 is equal to work divided by 0.30. 0.30. What is that particular work? That particular work is nothing but equal to 200 divided by 0.30. Then what is the value you will get? It is 666.67 kilojoule, because from the heat engine. So this is from the heat engine. This is from the heat engine. And this is the answer. But sometimes what it is there that, and I will discuss simply here. Here the refrigerator is okay. Here the refrigerator, that means this particular solution is okay. But sometimes if this system, if this system is used as a heat pump, if this system is used as a heat pump, how many megajoules of heat would be available for heating for each megajoule of heat input to the engine, right? So the under the same operating condition, but here let me put right, under the same operating condition, if instead of a refrigerator, if the heat pump is working, if the heat pump is working, right, then how you are going to sort it out? The COP of a heat pump, COP of a heat pump is equal to, is equal to, so here the desired effect is this one. So the desired effect is Q1 here. So Q1 divided by W. What about the COP? That is the COP of a heat pump is equal to COP of a refrigerator plus 1. COP of refrigerator is 5 plus 1. That means COP is 6. So COP is equal to 6, right? And what you are going to do, that is here, what about the work? That is Q1, that is Q1, and divide by W. What is that particular W here? The work output. So what is the work output you will get? Instead of this particular case, then you have to calculate here that particular work output. Say for a heat engine, for a heat engine, that is 1 megajoule of heat must be, that is heat input to the heat engine is 1 megajoule. Heat input to the heat engine is 1 megajoule. But what about the work? So that is the work is equal to 1 megajoule into the efficiency, the thermal efficiency. It is 0.3 megajoule, or 1 megajoule into 0.3. 1 megajoule into 0.3. So you will get it as 300 kilojoules. 300 kilojoules. So Q1 divided by 300 kilojoules. So what you have to do is, that is a heat engine is to be connected to the refrigerator. Then what about its performance? Instead of a refrigerator, if the heat engine is connected to the heat pump, then how the parameters are going to change? So from this case, the Q1 value, which you can get it as a 1.8 megajoule. 1.8 megajoule, right? So using an engine of 30% thermal efficiency, that is a heat engine, right? So try to understand this particular problem. This is the heat engine. Thermal efficiency is 30% to drive a refrigerator. So this is going to drive the refrigerator. Having a COP, see here. What is the heat input into the engine? That is to this one. For each megajoule of heat is removed. So here, this is what it is removed. So first you have to make the calculation for this particular case, right? For this particular here, and here it is, in this particular case, you can get it as that is 1 divided by, that is the not 1, that is W divided by 1 megajoule. So it is 1. So that is the work input is equal to, that is the 0.3 into 1 megajoule. So that is equal to 300 kilojoule. So this is what. Now, whatever the output, that is 300 kilojoules is getting from the heat engine, and that it is to be connected to the refrigerator, solve that problem. Instead of a refrigerator, if you replace the refrigerator with a heat pump, solve the problem so that you can get the answer. Okay. Hope this particular thing. So sometimes the problems are going to be very tricky. So try to understand how the connections are to be placed. See, when the heat engine is connected to the refrigerator, then what is its performance? In the same way, when the same heat engine is connected to the heat pump, then what about its performance? Because already we know that the COP of a heat pump is the desired effects are changing. So the desired effects are changing means COP of a refrigerator desired effect is different. COP of a heat pump desired effect is different. So once these desired effects are calculated, then COP of a heat pump is equal to COP of a refrigerator plus 1. So that is how you have to apply the concept. That is how you have to apply the concept. So now the household refrigerator, a household refrigerator is maintained. So now here the problem is going to look big.